All right. So everything from here is going to be recorded. Um, yeah, I was doing some research on how to manage the feeling of overwhelmed. It has nothing to do with your up and coming second exam. Just wanted to make it clear that was not the reason why I was researching.
Could be. You know what the second exam is?
Yeah, I just sent out a announcement today.
It said Thursday, so I'm assuming it's that Wednesday or the
It's going to be
following
next
Wednesday.
Thursday. Oh, next Wednesday. Sorry. Yes, next Wednesday. Sorry. Yep. Okay. Off by day. Sorry. I'm thinking that would be the case, because I want to kind of stagger, and so they don't fall on the same day. So we'll be talking about the second. We'll be talking about the second exam from spring semester in 440 today. Yeah, we're at that point for 440. We have been ready for some time. So let me. All right. All right. So I was trying to get into Canvas so I can show you the announcement for today, and of course it's not cooperating. All right. So okay, just refresh. Nope, doesn't like this login. All right. So is there anyone else I can borrow? Nope. Okay, fine. It could be my Wi-Fi connection because I found that sometimes my Wi-Fi would just kind of drop out for no particular reason, and I just reconnected through my Wi-Fi. Hmm. All right, well, all right, so that's okay. I don't really need to get back to Canvas because I know what I'm supposed to talk about today. Those will be the conditional branch instructions. So as long as I still have access to this page, I will still be okay. So what we're going to talk about first is the row that is currently being highlighted. That is the JMPI instruction, and the I really just has to do with the immediate. In other words, you tell the jump instruction where you want to go using the immediate operand. But when you look at the actual register transfer language description, which is in column C, it is mysteriously simple because some of the other ones like LDI is like there are a few steps to it. Even compare seems a little bit more difficult or it has some computation in it. This one just says the program counter gets whatever the program counter is currently pointing to. That's it. Okay. So you go like it cannot be that simple. I mean, jumping and continuing to another place of execution cannot possibly be that simple. So what we'll do is we're going to look at a sample program first, and then what we'll do is to kind of single edge through the execution of that program. So this way we can actually go through the whole processor thing again, and another chance for us to get familiarized with all the different components of the processor. So what I'll do is I'm going to start this with a no-op instruction. And the reason why I want to start with a no-op instruction is later on, I want to show you a tool that you can use to kind of track down the execution path and also the effects of every single instruction as you run your program through TTP. So that's why we start with the no-op. And then we have a JMPI instruction to a particular label. Well, just call this L1. And then I put a halt instruction here, and I put L1 over here, and I put another halt instruction over here. So this way, I have two ways to terminate the program, or so it seems, but the program will always terminate the program on line 5 because it cannot reach the halt instruction on line 3. So that's kind of the whole point of illustrating what JMPI is going to do. So if you go to the Assemble tab, you will see how the program is assembled. No op is just has an opcode of 00. We talked about this already in this class because it really is not an instruction on its own. There's no intent to make 00 an opcode. However, in the ROM, address 00 corresponds to Which cycle again? And when we execute instructions? The fetch cycle, very good. Okay, so because location 000 of the ROM corresponds to the fetch cycle, so that means we have a quote unquote free instruction called no op. Because it will basically, after this instruction gets decoded, where do you think it's going to go in terms of the ROM? Do you guys still remember the decode process? We take the opcode, we left shift it by 4 bits, that becomes the location in ROM that we need to go. So if the opcode is 00 and we left shift by 4 bits, what is going to be the result of that? It will be 000, 3 zeros, okay? So the microcode pointer would end up with 000, and the microcode pointer is connected to the address port of ROM, so that means we're just going to go straight back to location 000, which is starting another fetch cycle, right? So that's why the no op instruction, which has an opcode of 00, is basically a free instruction. It's not intended like that, but it just kind of works out that way. So the second instruction is JMPI-L1, which is this instruction here. The opcode itself is just 40, and then this 04 has to do with label L1 having a value of 4. The reason why label L1 has a value of 4 has to do with counting. Because if you go back to the source code here, we can do the counting by hand. This one takes up byte 0, this one takes up byte 0, byte 1 and 2, byte 3, and this is byte 4. And that's why label L1 corresponds to the address of 4, which is just a value of 4. Whether you wanted to call it 4 in decimal or 04 in hexadecimal, that's just a base, change of base. All right, so let's go ahead and go to the RAM file tab, and then we go to File, Download, CSV, and we'll call this jmpi.csv. And then we'll run it in the simulator, which is already loaded here. Control R resets everything, and then go to the RAM component, right click, and then click on Load Image, and then give it a name, which is jmpi.csv. And now we have the program here. So I'm going to go fast, with the first few edges because that's all familiar already. And I'm going to stop when the microcode pointer is 400, which is corresponding to the location of ROM that actually implements the JMPI instruction. So are there any questions about what I just said? Are those terms okay? No clarification needed? Okay, so we'll go ahead and do this. So Control T, Control T, Control T, Control T, and this is the execution of the no op instruction. It gets us straight back to the defetch cycle, the fetch cycle. So we fetch again, but this time we are fetching the 40 instruction, which is the JMPI instruction. You can see how the instruction register is now 40. And when we decode this, which means when we look at the falling edge, we're going to have a rising edge first. But when we look at the falling edge, the microcode pointer is going to go to 400 because that's what decode does. So Control T, Control T, there we go. So now we pay attention because now we want to look at the actual implementation of the JMPI instruction. How does it get a job done? Now with this one, because I already talked about the RTL or the Register Transfer Language Description, we can now just kind of focus on how it gets the job done because we already know what it is supposed to be doing. So we can see the RAM is active. We are reading from RAM, and now we look at the address port. At the address port of RAM, it's coming from the multiplexer as usual, and we can see that the select is a 1, so we are connecting from input 1 to the output, and input 1 comes straight out of the program counter or PC. So now we know that we are getting to we're reading a location in RAM, and the address is provided by the program counter. So that explains the star PC, of the RTL description. So the next question is, who is going to be updated using the output of RAM? So now we track down the data port of RAM. It goes to many different places. So one of the places that it goes to, and you can see most of the places that you go to really do not matter because the instruction register is not enabled, so it's not going to change. The register bank also has its input enable being turned off, so none of the registers inside the register bank is going to be updated. However, we can see that the program counter is enabled, so that means the program counter will update on a rising edge. So now we have to track down who is supplying the data for the program counter to update. So the first thing is we look at the D port here. We go to the multiplexer. The multiplexer is selected by PCMux. And PCMux for now, we just say, oh, okay, since it's a 1, we are selecting input 1 to connect to the output. This input 1 is coming out of this particular multiplexer. And this multiplexer, in return, also has a select of 1, which means the highlighted node, which is coming straight out of the RAM D port, is connected to all the way to the program counter. So I have just explained how I established the path from the D port of RAM all the way into the D port of the program counter. And because the program counter is enabled at this point, so that means on the rising edge, the program counter is going to be updated by whatever the D port has in RAM, and that in return is reflecting the content at the location that is pointed to by the program counter itself, which is why the description of the JMPI instruction looks like this, because I'm using the program counter to point to a location in RAM, and the content of that location in return is used to update the program counter. So I'm going to pause here and see if there are any questions about what I just said. Obviously, if I do another control T, you will see the program counter getting updated to 04. But right now, I just want you guys to see if there are any questions that you want to ask about how all of this is happening.
So basically just saying, go to this place.
Hmm?
You're telling the counter to go to a
I'm
certain spot.
I'm telling the program counter to go to the spot that is indicated by the byte after the 40 opcode, which in this particular program, if you look at the assemble tab, this 04 is where the program counter is supposed to go to.
And just because of that, because um, the label that we have that's the byte of memory that it has, correct?
It's because because the assembler is when it parses JMPI and then L1, the assembler is responsible to look up, okay, what is the opcode of JMPI? Well, that turns out to be just 40 because JMPI itself does not depend on any register.
Right.
It doesn't depend on register A, B, C, or D.
Right.
So it's just a constant of 40.
Right.
But the second part of a JMPI instruction is, okay, so you want me to change the execution path. Where to?
Right.
Right? So that's why you need a second byte to indicate which location do you want me to go to.
Right.
So that's why the JMPI instruction has 2 bytes.
Mm-hmm. And just to clarify the second part, that the label that we created, L1, that sits at memory spot, or I guess.
Not entirely. A label has no presence when you execute a program. In other words, when you go to Logisim over here and go to the RAM component, there is no such thing as L1. L1 as a label is a assemble time construct to save you the trouble of having to count, where is that halt instruction that I need to go to again? It's 1, 0, 1, 2, 3. Oh, that's location 4. So the purpose of a label in this case is to save you from having to count the number of bytes so that you can specify the correct address. Is that making any sense?
It makes sense, yes.
Yeah. So it's an assemble time construct, but it's not a runtime construct. At runtime, when you look at TTP, there's no such thing as L1. There's only 04.
Right.
Because L1 is just a symbolic name of 04.
Correct.
Exactly. And in this case, it is a location, yes.
Okay.
So in this context, L1 is the location of the halt instruction that we want to go to.
But it doesn't have to be a location?
It does not have to.
What
It's
else?
just an integer. I mean, L1 is really just an integer. In this case, it is defined by where L1, the definition of L1 is, and
Right.
therefore has a value of 4. So as far as the assembler is concerned, all it says is every time I see L1, replace it by 4.
Okay.
But you can use it for calculation if you want to.
Mm-hmm.
You can use it for other purposes, if you want to.
Gotcha.
It's just saying that, well, every time I see L1, it means 4. But what do you mean by 4? Are you adding 4, subtracting 4? Are you referring to location 4? It doesn't matter. The
Just
label
whatever
does
you
not
choose.
has it doesn't have a type associated with it.
Okay. Cool.
All right. Very good. Okay, so now we are ready for a rising edge. So that means we are going to observe that the program counter would update from 02 to 04. So Control T right there, and you can see how the program counter indeed updated from 02 to 04. And that's the action of the JMPI instruction. So when we have a falling edge now, that will basically make the microcode pointer to advance to location 401. And 401 is going to contain the 1 bit on bit 25 here of 1. And it's going to force the microcode pointer to reset back to 000, in which case we go to location 04, fetch the halt instruction. And once we decode the halt instruction, that's the end of it, right? Because the job of a halt instruction is to halt, to stop. And I cannot stop this, mental image of a British police person, with a traditional hat, holding a club and say halt, and then blow the whistle, halt. That's what the halt instruction does. It halts. So are we good so far? Are we understanding the JMPI instruction? So might as well just do that once, right? So Control T. We are now back to the fetch cycle because the microcode pointer is back to 000, and we are about to have a rising edge. And you can also see where we are getting the opcode because we're getting the opcode from location 04, and then this 01 as a content at that location is the opcode of the halt instruction. Are we doing okay so far? Yes? More or less? Okay. So let me give you a program that I am not going to execute, but nonetheless, I think we should just kind of think about it, and you guys can tell me what it's going to do. So I'm going to change this instruction here to JMPI L1 also. What do you think this program is going to do? We will indeed get to line 5, which is another JMPI instruction, but where do you think it's branching to? It branches, well, I mean,
It's just go back up to before, right?
not even before, back to itself. So this is a very tight loop because you're asking a JMPI instruction to go back to itself. Okay, so this is the tightest loop you can write in assembly language, is to have a jump instruction to jump back to the beginning of the jump instruction itself. So without even looking at the opcode, what do you think? Well, actually, it's not going to be too much fun, but what would be the 2 bytes corresponding to the JMPI L1 instruction here?
Byte 1 and byte 4.
You mean the location?
Oh.
So location-wise, yes, it is 04 for the JMPI opcode and 05 for the L1 itself. So L1. So what is the value of L1? Is this changing the value of L1 by changing this instruction from a halt instruction to a JMPI L1 instruction? Does that change the definition of L1?
I would say no.
You're correct. It does not change the value of L1. So this particular JMPI to L1 instruction will still be implemented by the same 2 bytes, which is 40 as the opcode of JMPI, and then 04 because label L1 has a value of 04. And we can verify by going to the Assemble tab, and you can see how the two JMPI L1 instructions are exactly the same. Is that okay? Are we feeling comfortable with the JMPI instruction?
Because it's just a pointer, correct? It just says.
It's a in C++, this is equivalent to a go-to statement. There is such a thing called a go-to statement in C and C++, and most other programming languages too.
Mhm.
It's just a taboo to use the G word.
No, why? I guess. Okay.
You can ask your professor in structured programming why it is a bad idea to use the G word or the G statement. And can anyone guess, okay, from what you have learned in CISP300 as well as 360, why do you think it's a bad idea to use a go-to statement, which allows you to go from any place within a function to any other place within the same function, as long as you define the label as the landing place, as the spot to land?
So you can have an infinite loop that way.
You can do a lot of fun stuff. You can be inside the conditional statement, inside a loop that is inside another loop that is inside another conditional statement, and you can jump all the way to the middle of another block of statement that is part of another loop that is another of inside another conditional statement. It allows you to go anywhere from anywhere to anywhere within a subroutine, within the function. So why is that such a bad idea? Because this looks like a lot of flexibility. Isn't that a good thing?
You can blow up a computer like that, right?
No, no, you won't blow up a computer. Well, it depends on how you branch. I mean, if you perform a forward branch, sure. I mean, it's not going to cause a problem because you can potentially end up with an infinite loop if you branch backwards, which means the label is defined before the goto or the JMP instruction. But if you branch forward, that should not be too big of a concern. It makes the program much more difficult to analyze. That is the problem. Because normally, how do I know, after I get out of a loop, what is the condition right after I get out of the loop? The way I do it is I look at the condition of the while loop and say, right now here, I know the condition of the while has to be false. So that's one thing that can help me understand by the time I get out of the loop, to continue after the loop, the condition of the loop itself has to be false. Does that make sense? But if you use goto to get out of a loop, that doesn't work anymore. That logic does not work anymore because you can just say, I got this special reason here to get out of the loop. So even though the condition that I specify in the while loop is not false, but since I got this special reason here, I'm just going to get out of the loop without even getting back to check for the condition of the while loop itself. So on one hand, it seems to give you a lot of flexibility. On the other hand, it is too much, way too much flexibility. It turns programming into non-structured programming. It has a name that is named after a food item as well as a deity. So what is that name? How do we call code that is difficult to understand because it goes from this place to that place and then back to this place and back to that place? Spaghetti code, yes. Okay, so we do not want to write spaghetti code because spaghetti code is difficult to debug, difficult to understand, and difficult to change if you need to add features to the program. It becomes almost impossible to do that. Are we doing okay so far with these concepts? But in assembly language programming, you don't have any options to not to use goto because you do not have if, you don't have while, you don't have do while, you just have conditional branches. Now, what we are seeing here, this is unconditional. In other words, every single time you get to line 2, it will continue execution at the label L1. It is not conditional. It doesn't say, sometimes we're going to do that and other times we're not going to do that. It's always going to do it. So this brings us to conditional branches. So let's go ahead and change the program a little bit, and this time we talk about conditional branches. And I don't think I need a no op for now, so I'm just going to use JCI as the first instruction So it's going to go to label L1, and this time I have a halt instruction here, and then when we get to L1, we have another halt instruction here. So what is JCI and how is it different from JMPI? We go to the opcode table, okay? So when we go to the opcode table, we take a look at JCI, and then we try to find out what it's going to do. And you can see that, it has the same component as JMPI, but not all the time. Because this is a ternary expression, which means it is a conditional statement compressed into an expression. What it is saying is, if C is true, in other words, when C or the carry flag is a 1, then it behaves just like a JMPI instruction. Whatever PC points to with the reference, and that becomes the new value of the program counter. On the other hand, what happens when the carry flag is not true? Well, we go to the else statement, which is basically just saying, in the other case, just increment program counter by 1. Is that okay? So this is conditional because it is conditional to the value of the C flag, which is actually both the carry and also the borrow flag. Okay, so we combine those two into one single flag. All right, so now the question is, how does it work? Because at this point of this class, we're still concerned about how instructions work, okay? In addition to what they do, we want to know how to get the job done. So now we go to the Assemble tab or the RAM file tab, because we can now just go ahead and download this whole file, so I don't have to type in the entire thing by hand. So you go to download. This program is jci.csv because I just want to name the file under, after the instruction that I want to illustrate. And then we switch back to LogiSim, reset the processor, Control R, and then reload RAM content with the new program, which is CSV. Oh, nope, it's jci.csv. There we go. All right. So in this case, we want to get to the ROM location corresponding to the opcode of the JCI instruction. You can see the JCI instruction has an opcode of 44 as an opcode. So that means location 440 in the ROM is where I'm interested in. So I'm going to skip, I'm not going to skip, but I'm going to just kind of quickly go over the fetch and the decode, okay? And then the focus is what happens at location 440 in ROM. So here's fetch, auto increment of the program counter, decode, and now we're at location 440. Excuse me. All right. So what is special about this instruction here, or this particular bit pattern in the ROM that controls the rest of RAM, the rest of the processor? Well, we see RAM is being turned on. It is a read cycle again. And we will also see that the program counter is about to update. Okay, you go like, so what's new? Okay, seems like there's nothing new here. In fact, if you look at how we are updating the program counter, you would go like, okay, so how is it different from last time? Well, this time the PC mux is dark green, which means we are reading from input 0 to connected to the output, and this is just auto incrementing. Then you go like, well, so it is as if the instruction is not even here, because all it wants to do is to continue execution with whatever is next to this. But that's only because the carry flag is a 0. The carry flag is bit 0 of the flags register. This is the flags register here. You can see how its content is 0, 0. So when you have a content of 0, 0, you don't even need to know where bit 0 is. You know it is going to be a 0, right? Because all the bits they all have to be zeros. The carry flag is bit 0 of the flags register. So if I want to just turn on or make it a 1, what do I need to type in here? I just want the carry flag to be a 1. The carry flag turns out to be bit 0. So what do I need to type in here in order to say, well, let's just kind of inject a 1 into the carry flag? 0, 1. Okay, very good. So I just type in 0, 1 on the keyboard, and now the carry flag is a 1. So now we can see how this is affecting the instruction or affecting how the program counter is getting updated, because we can now see the program counter it's still connected to the multiplexer, but this multiplexer now has a 1 coming from PC Mux. So here's the question. It's like, how does PC Mux get changed just because we changed the value of the carry flag in the flags register? So the first thing you would probably know is, I'm suspecting PC Mux is not coming from ROM directly. And why do you think that would be a reasonable deduction? Okay, what I did was I changed one of the registers, which is this one over here. That's the design hub thing. Um, I'll read that later. So let's put that away. Oh, okay. So I changed one of the registers, and it changed the tunnel that we call PCMux. If PCMux came from the ROM data port, it would not have changed. It would have stayed exactly the same because ROM. ROM is read-only memory. I'm gonna turn off this cord on this side. Just give me a second here. Oh, that's the wrong one too. I almost exited OBS instead of Discord. There we go. Discord is gone. All right. So if it did come from ROM, it would not have changed just because I changed the state of one of the registers. So that means PCMux is not coming straight from the ROM. But we also know the behavior of the processor should be dictated by everything that's coming out of the ROM. So now we should be curious, right? It's like, how did this get implemented? In other words, where is PCMux? Because it is not coming from ROM, so where can it come? Where can it be coming from? So you can find that PCMux is here. PCMux turns out to be the output of this multiplexer. And this particular multiplexer is selected by what I call PC MuxMux because it's a multiplexer that impacts another multiplexer. So if you look up MuxMux, okay, PC MuxMux, it is 0, 0, 0, which means it's using input 0 to connect to the output. Then the next question is, okay, so where's input 0 coming from? This is input 0 of the multiplexer. So input 0 is connected to a splitter, right? And that splitter says, this is bit 0 from whatever the merged end is. And then when you look up the merged end, where does it connect to? So when you look up the merged end, it connects to the output of the flags register. So this solves the mystery. In other words, this is why the update of the program counter is conditional to what the carry flag is in the flags register. Because the multiplexer up here is basically saying, PC Mux, you are getting your value from a flag, from one of the bits of the flags register. So as a result, this particular PC Mux here, which controls which end of the multiplexer connects to the output, that becomes conditional to the carry flag. Is that okay? I'm just gonna pause here and see if you guys are making all the connections. If you are to write down, okay, what is happening here, how would you write down what I just said? Yep.
Um, so we're talking about the carry flag, right? Or the C flag, and that represents it's represented there by the register flags labeled, right? And then when we change
So
that,
the C flag is bit 0 of the flags register.
correct. So
Yep.
when it's 0, 1, in this case, it updates that PC Mux Mux, the multiplexer.
Not directly. PC Mux comes from ROM. So this comes from ROM,
Okay.
but this part here comes from the flags register.
That one comes from the flags register.
Yep.
And it ultimately updates
PC Mux.
if it's a 0, 1, it updates the PC Mux.
Yep. Which in
updates
return,
the PC counter, correct?
No, not directly. So what PC must eventually do is it will help the multiplexer that is feeding the D port of the program counter. It basically says, well, if PCMux is a one, use this connection to update the program counter. If PCMux is a zero, then use this input to update the program counter.
Okay.
That is where the decision point is. So the factor controlling the decision is, in this case, I'm isolating to really just, bit zero of the flags register, which is the carry flag. That is equivalent to the condition of a conditional statement. Okay? It's just true or false. Okay? But how we use the true false to control, so how should we update the program counter? That is the job of the multiplexer. So so PC mux is the condition. This multiplexer is doing the job of a conditional statement. It's asking, okay, so which input connects to the output? How should I update the program counter? And then PC mux is the switch that helps us decide, oh, you should increment, okay, when the carry flag is a 0, or it will say, you should use the D port of RAM to update yourself, in the case when the carry flag is a 1.
And that's how we represent, that's, I guess, one of the ways we represent conditional statement in assembly. Just by that.
This is the only way to represent decisions in assembly language programming. Are we still doing okay so far? Maybe? Ish.
So there's 5 bits for the flag register? Or?
There are 5 bits to the flags register, yes. So the question, I'm guessing your question is, what are the other 4, right?
Yeah.
Very good. Okay, I like those questions because it reflects your thinking. It's like, I got a clue. We know what 1 bit is about. What about the other 4, right? So how do we track it down? So the way you track that down is to look at either the input or the output of the flags register and see where they go. So if you look at the input, it comes straight from the ALU. If you look at the output, it also connects to the ALU in addition to the multiplexer here. So that means the answer is probably, where do you think you can find the answer to that question? What the other 4 bits are about? Yes.
On the opcode table that we have here? Are you saying which flags those are, or did I misunderstand?
Exactly. What are those other 4 flags?
Well, I was looking at it. Just looks like it lines up with the information
multiplexer
here on the opcode. So the L flag, the A flag, the S flag, the C flag, and the Z flag.
Okay, so but I think the way we can find that out is looking into the ALU, right?
Yeah.
Okay, so now we look into the ALU, and then we locate the port that has all the flags connected. So how do we know which port is which port? Okay, this is something that we have learned already, but some of you might have forgotten. So you go to the appearance of the component, and then you click on the pin that you want to figure out, like that, and you can see how in the picture, the picture-in-picture, lower right-hand corner, it will highlight that particular pin. So we are looking at flags out, which is this one here, and that is the location where we need to look. Is that okay? So now we go back to main and we try to, oh, not main, sorry. We are going back to the ALU and switch back to the component view. So we are now looking at this thing here, right? So it has got 5 bits, okay, because we can see the splitter says 0, 1, 2, 3, 4. And when we track down bit 0, it is C out, and C out is connected from the multiplexer. This multiplexer is going to use the same operation select, which means input 0 comes from the adder. It's the carry from the adder. Input 1 corresponds to the borrow of the subtractor. And then input 2 all the way to 7, they are just going to C in, which means we're not updating anything. We're just copying from whatever the carry flag is at this point. We just copy that. No update. Is that okay? And then we look at the Z out. This is Z out. So Z out comes from here. This is Z out. It is the output of a NOR gate. This NOR gate has 8 inputs, Each input corresponds to 1 bit of the result of the operation. So that means the Z flag is going to be a 1 if and only if the result of this operation is a 0. Now, does it depend on which operation that we are adding, that we are subtracting, that we are shifting, or we are ANDing, or we are NOTing? Nope, it doesn't matter, okay? It just reflects whether the result of an operation is 0 or not. That's all it's going to say. Is that okay? What about the other 3 flags? Those 3 you should recognize. This is the sign flag of the output, which is also what we see as the sign flag of the difference in the subtraction. Okay, and why do we know? Because that's where it taps. Okay, see how it is using a splitter, but it's only paying attention to bit 7, which is the most significant bit of the result of an operation, and that becomes our sign flag. Are we doing okay so far with what the sign flag is? So what about the other 2? This is O flag, and this one is the exclusive OR between the sign flag and the O flag. How do we call this one? I did not give it a name here, but we did give it a name when we talked about binary comparison. So what would that node be if I were to give it a name?
L flag?
It's the L flag. Very good. Okay, so the L flag is the exclusive OR between the overflow and the sign flag. So out of all of these, the one that is more difficult to figure out is the O flag. So when you look up the O flag and see and ask where it's coming from, the O flag is coming from this multiplexer. But this multiplexer basically means if it's not an add or subtract, we'll just copy the O flag from whatever it used to be. So when it is a subtraction, it's coming from this particular node, and this is an OR, this is an AND. Every time you see a bubble, it is a NOT. So this is the same thing that we saw when we looked at binary comparison.
That long equation?
Yeah,
That's the O flag represented.
that is the O flag represented by connectivity of gates. All right? So, with this all said and done, how do we make use of the JCI instruction? Because obviously by itself, okay, let me switch back to the assembler. Because by itself, like something like, oh, I thought I wrote a program with a JCI instruction. How is it reverting back to this one? I must have typed Control Z accidentally. That is mysterious because I probably did that. Didn't I change the instruction to JCI?
I think you did. Try to hit redo.
Yeah, let me see. Nope. You put a halt instruction here. That is mysterious. Halloween.
You think that like last edits, and then you can probably pull it back up from there.
Ah,
That way you're not having to.
but if I have undone it,
It'll keep track of all the
Oh.
edits made.
Okay, we can do that. But the first thing is I want to double check to make sure that whatever program I load here is JCI. This is definitely JCI. So we go back to the browser and look at this.
No, where's this last was edit? You see that where the next to where it says help in assembler,
Ah,
and then you should be able to see the changes. So you can poke around on the side and see if it'll pop up, and then you can hit restore this version.
oh, okay. It's probably be one of the items but under the drop down.
Yeah.
Wow, it's a powerful tool.
Oh, it is. I think I have lost it
Maybe,
in several sense of that word
maybe
phrase.
10, maybe 1036.
Um. Well, okay. Everything is recorded, right? So I can actually go back to the video recording and figure out how I accidentally lost it. Both the program and my own sanity. Yes.
Shows the correct one on mine.
Hmm?
Shows the correct one on mine.
On yours. So maybe I have two assembler open. That's possible. Something is.
But it also says last edit was 2 minutes ago.
I see. I'm pretty sure I did something.
It'll be interesting to watch this lecture back.
Yes, it would be. I think I accidentally touched Control Z. But Control Z will only undo one of the lines. Hmm. All right. Well, it's a Halloween special. Oh, look at this. This is still JCI. So how come source is different? That is not good. That is definitely not good. Okay, so I might have broken the assembler. Okay, I'm just refreshing the browser, and the assemble tab stays with this one. That is really weird because it has this associated and then all of these empty lines here. Okay, now I need to actually, I think I lost internet connection. I think that's why. Okay, so let me,
The source and the assemble, they both show different things.
they do?
Yeah.
That is very, very strange. Alrighty. That's really strange because, that is, okay, because if I refer, I think I know, okay, that is not supposed to be like that. This is supposed to be an equation of some kind, so I must have typed over this portion. No, that is not right. That is just not right. I mean, something is seriously wrong here. I still got my equation here, and I still got my equation here, but the assemble tab does not have those equations anymore.
What if you go to the last edits again and then just go back to the beginning of the class?
Restore it all the way? Yep.
Restore it all the way.
Yeah, Shift Control Alt H is the quickest way to go back to history.
And you can do it from,
Yeah, from Thursday,
yeah,
and say restore this version. All right. All right, so we can see the equation here. So it must be me typing on the wrong tab. Hard to say. Okay, so let's see if this still works. JCI to label L1, and it's going to complain, which is fine. This is L1, alt again. All right, so now we get to assemble. Everything is back to normal. I think I overtyped here. I don't know. It's just strange. Well, if I type in the wrong tab, I would not be able to get to the right RAM file. So it's just, okay. I cannot explain it right now. I will try to figure it out later. All right, so let me see what else I need to talk about. Right, tracing the program, okay? Let me see how much time I got here. I got about another 30 minutes. Okay, so I have a few options. So how do you debug a program when you write longer programs, okay, in TTP? So that's the question. How do we debug a program when there's no debugger? There's no GDB here. You cannot just right-click on the line and it sets up a breakpoint. So the way we debug a program in TTP or in Logisim is we keep track of the value of the registers. Okay, and there's a way to do it. So I'm going to show you what you need to do for today's lab, and then if I have time, I'll give you a much more generalized method to debug your program. All right, so we will keep the same program. Okay, so we're going to look at this program again, and we want to figure out, how the program ended its execution. So what all of this has to do with Logisim. So in Logisim under Simulate, there's a feature called logging. So logging, once you get to logging, it will ask you what do you want to log. And basically what it will do is it will generate a new line of log every time something that you're watching that you specify here has changed. So let's see. So let's just say that we want to look at the program counter. Okay, so we want to say every time the program counter changes, we are going to add an entry to the log. So when you add something to the log, you have a choice of what base you want to use. So you can change the radix, which is the base of the number. Right now it is in base 2. You can change it to base 10, which is decimal. You can also change it to base 16, which is hexadecimal. I personally would prefer hexadecimal because that's what the assembler also uses to reflect the addresses. So I'm going to change it to 16 as hexadecimal. And then you can add additional items, in addition to the program counter, if you want to. You can also, add, like the halt or the instruction register. Okay, so you can add more items. Okay, and change the radix again to base 16. And I think that is 16 right now. Yep, there we go. So you can add as many items as you want, okay? But you don't want to add too many because otherwise it becomes much more difficult to read what you're dealing with here. And then what you can now do is to go to either table or file. If you want to keep all the logs, within Logisim, you can go for table, which is by default. Or if you want to, log everything to a file, then you can go to file. Is that okay so far? So depending on how long the trace is, if the trace is long, I would definitely go for file instead of table. Because otherwise, you're going to have to eyeball everything. If you go to a file, at least you can open up a text, a notepad or something like that to help you keep track of things. So let's say you want to use file. Then what you need to do is to go to select and specify, a file that you want to contain the log. So I'm just going to say JCI dot TSV. So TSV is the abbreviation of tab separated value. So there's a reason why in this case I'm going to use TSV instead of CSV because tab separated value is the format that that's how the log is generated. Okay, so I will show you why this is useful later on, but for now I'm just going to say, yeah, I'm going to save it to TSV. So you click save, and now, if I do anything with this processor now, it's going to be logged. All right? So the first thing I'm going to do is to reset the processor, but I don't want to lose the content of RAM. I can close this window for now. And the way to do that is to hit the reset button, but not the Control R reset. So there's a reset button here. The key is when you hit the reset button, you want to make sure the clock is low. Okay, I tried to come up with a circuit to do that, but there's no easy way to change the state of the clock when I hit the reset button. So you just have to kind of make sure the clock itself is dark green, and then you can click the reset button. So you can see how everything is reset, except RAM is not zeroed out, because then I don't have to reload everything. So now I can start to log the program. I can execute the program. And for this particular step, I'll use Control K, which is enabling the auto take. Okay, so you can see the program has now halted. I know the program has already halted because the halt pin is a 1. I type Control K again to stop all the clocking because it's not going to take the execution any further. So right now I have a file called jci.tsv created in the folder that I told it to create in. Okay, so I'm going to head over there and take a look at the content at that location. I use a command line editor. You guys can use Notepad. So let's go there. So here is the file called jci.tsv. And this is the content of that particular file. So every time either the program counter or the instruction register is changed, it creates a new log entry. The first line has to do with executing the first instruction, the initial condition, which read, let's see, that's the first time the program counter, well, not sure exactly why it logged the entry, but those are the initial values. The program counter started with 00, and then the instruction register also started off with 00. And I know why it is creating that log entry, because I started the logging before I reset the processor. So that means the instruction register changed from whatever it was before back to 00, and that triggered a new line of log, so it became the first line. The second line, is when I fetched the JCI instruction, because we can see the instruction register became 44. And then the third line is when I auto increment the program counter. So you can see program counter changed to 01 from 00. The fourth line has to do with when I execute the JCI instruction, because the carry flag is automatically reset to 0 as well. So that means we are not branching to where we specify in the JCI instruction. Instead, the JCI instruction just continue its own execution, and that's why we end up at location 02 because of the auto increment of the program counter again. And then this one here is because of the fetch cycle of the next instruction. So I'm fetching the opcode on at location 02, which is a halt instruction. And then the last line is because after the fetch cycle, there is an unconditional auto increment of the program counter. So the program counter got incremented to a 03, but we are actually not fetching from 03 anymore because that's just the auto increment, which is unconditional. So that kind of explains all the things that went on when we executed this program. Are we doing okay so far with this? All right. So let's just say that you want to log the whole thing again, but this time we want to inject a value of 1 into the carry bit to see how it changes the execution path. Is that okay? So let's go ahead and do that. So we'll go ahead and in LogicSim, first of all, we want to reset everything. Now remember, logging is still on right now, okay? So if you don't want things to be logged at this point, you can go to logging, you go to file, and then you just disable it. So now with logging all disabled, I can now tweak things the way I need to tweak it and run it again later on. First thing, this time clock is a high, so I need to change it to a low again, and then I can hit the reset button, and I still retain the content of RAM in this case. So I'm not quite ready to run it yet because I also want to inject a value of 01 into the flags register because I want to see how the execution path changes when the flags register has its bit 0 being a 1. So now I'm ready to go again. So I can go to simulate, go to logging, and I can re-enable the logging. The problem is, if you do something like this, it's going to continue to spew the output and append to the end of the current log file. Let me say that one more time, okay? If you do not do anything special, it will only append the new log entries at the end of the file that you have specified. Is that okay? Now, if that is the intention that you have, that's fine, okay? On the other hand, if this is not your intention, and you want to reset the file and start from scratch again, then you have to do something. So I'm going to first illustrate what I mean by, it will just append to the end of the current trace, okay? So I'm just re-enabling it, which means it is now re-enabled. I close window, and I type Control K on the keyboard to start another trace. Control K, we get to the halt instruction, Control K again, go back to the file. And you can see that this time it looks very confusing because this is the starting point of the second trace. This is the starting point of the first trace, but they combine into one single trace. It makes it much more difficult to understand, but what just happened with this particular run of the program? Is that okay? So most of the time, this is not what you want to do. Most of the time, what you want to do is to start from scratch. So I'm going to teach you how to start your log file from scratch. We ready for that? Yep, okay. So you might want to write down the time because your lab actually includes, it includes a part that requires you to reset the log file. So we go to simulate again. Okay, let me make this the main window here. We go to simulate, we go to logging, we go to file. So to reset the file, all you have to do is to reselect the file. So you go to select and you say, yep, that's the file that I want. Click save, and it will ask you, do you want to overwrite do you want to append? The answer is I want to overwrite. There we go. So this time, when I rerun the program, which means I'm going to use the same approach as last time, clock is low already, click the reset button, and I'm ready to control K. So control K, and the program has already halted because I can see the halt pin is a 1. Control K one more time. This time, when I go back to the editor, you can see how it has changed. This is just starting from scratch. Is that okay? Does everybody understand what I just showed you? All right. So there is one part, which is the last portion of the lab today, that will require you to change the program just a little bit, and then trace again, and then do a bunch of counting. So that means between each run of that code, you're going to have to remember to re-specify the log file and overwrite the one that you have already created. Is that okay? All right. So the last part of today's lab requires you to do some counting. And it wants you to do some counting from the beginning of the entire program, every single time. So between the runs of the program, if you use the same log file, you want to re-specify the log file because otherwise it will do the append thing, which makes the counting very hard to do because you will see not only the trace of this run, but you will also see the trace from a previous run. But what I want you to do is to keep track of the count of the current run.
Okay, and should we include the 0000 line? I guess it's called the op or the.
Well, okay, so that is up to you. Okay, what do you want to include in the log? It's up to you because that's part of what the lab is to have you to think about what is important to log.
Gotcha.
And when you read the question, it will be clear what I want you to count.
Okay.
But the question is, in order to get that correct count, what do you need to trace in the processor? What matters and what do not matter? Okay, so I'm looking at the clock. We still got 15 minutes. So I'm going to teach you a different way to do the same thing. And the first time you do it, you're going to go like, oh, this is difficult. I'm having a really hard time to do this. But the more you do it, the easier it gets. And there's also a special tool that semi-automates the whole thing. But to set up the semi-automated process itself is going to take some time. Okay. All right, so we'll go back to this one here. And this time I am going to close the GUI part of this. Okay, so close the GUI because this method only works when you are not using the GUI method. Okay, you still need the assembler. So in the assembler, this time it is important to start with a no-op instruction. So I'm going to start with a no-op instruction. And I will make this an entire complete program. So I'll do LDIA with 6, LDIB with, say, 7, and then we'll do a CMP, which is compare AB. So CMP AB is just going to do the A minus B. It is just going through the subtractor of A minus B. And then I have a JCI instruction to label L1 again, a halt instruction here, and then another halt instruction at label L1. All right, so this program is self-contained. I don't need to tweak the flags register manually because the compare instruction is going to do something to the flags register. Okay, so this is the program that I want to run. I go to the RAM file tab. I still have to do the download here. So we'll go ahead and download as a CSV. And this is going to be, I call it CMP, okay? cmp.csv, and I think I put it into the temp folder. So here's the part that might take some of you a little bit of time to kind of get used to, is you have to run the entire thing from the command line. Now, if you have run Logisim from the command line before, because in the first week, remember you got some homework assignments where I give you a tester and you can run your design through the tester to make sure that all the outputs are correct. If you went through that process, this is very, very similar, okay, with only one minor difference. So I'll show you exactly how to do that from the command line. So in my case, all my stuff is under document CISP310 under processor. So this is where I find my jar file, my circuit file, and so on. So my command is going to be Java, JAVA -jar, and then the logisim 310.jar. So that will start up logisim, which is not completely what I want. Okay, so I have some additional stuff, and then specify processor 0004. So this will start up logisim in GUI mode, and it will preload processor 004. But that's also not what I want to do completely. So what I want to do now, I think it is a load. So what load does is it will ask for a file name, and it will put the content of the file into the RAM component of the processor automatically. So you don't have to right click on the component and then say load load file. So that file is in temp. It is called, I think, cmp.csv this time. And then you want to use the same thing as a table, dash tty, and then table. And you can just press the enter key and see what happens. Okay, I promise you, your computer is not going to blow up. Nothing bad is going to happen. Okay, well, nothing too bad is going to happen. Okay, so it gave me an output. Okay, you look at this output and go like, what the heck is this output? Well, it's logging all of the output pins, and I don't think it logs all the registers, but it automatically logs all of the output pins, which is a whole lot, right? So if you want to dig through this, it's not going to be easy. Okay, I certainly don't want to dig through this to find out what happened when I ran the program. So what you do is you capture that. Okay, the greater than symbol here is called redirecting. So instead of printing all the output, which is useless to me because I don't want to manually go through all those zeros and ones. So I'm capturing all the output here into a file. You can call this file anything you want, but I'm going to call this file cmp log.tsv. Because it is a log file, it is still a TSV, which is a tab separated value file. So do this, I created a file. So now the question is, but how do we know what happens, how to decode that file? Because if I use a text editor to look into that file, it's difficult for a person to understand what is going on here. Just a whole lot of zeros and ones, right? So the way you do this, the way you decode the log file in this case, now this is the part where you go like, really, do we have to do all of this stuff here just to get it done? So you need to go to the trace log data tab, and then you go to file, you go to import, and then you go to upload, and then you choose the log file to upload. So in this case, it's under my temp folder called cmp log.tsv. Press the enter key. It will ask you a bunch of options. Now, this is where it's also important because what you want to do is to select replace current sheet for the first one. You go to selector separator type. You want to specify tab. Do not let the spreadsheet decide on its own. And you also want to turn off convert text to numbers, dates, and formulas. The current time is 11:40 because I know some of you may want to get back to this screen just to double check to make sure that you got all the options specified right. And then you can click, finally, you can click import data, like so. It's going to take a little bit of a moment, and it would import the data, which is not very meaningful to you because it's basically the same zeros and ones in the TSV. And then we can now go to the analysis tab. And the analysis tab is nice because now it shows me the first instruction, start execution at location 00. It has no side effects whatsoever. It did not impact any RAM. It did not change any registers. It did not change any flags registers. The second instruction is starting at location 01. This is not too useful, but it does tell me that register A becomes 6 because of the instruction at location 01. Is that okay? And then we get to location 03. This part, once again, is not important, but it tells me that the instruction changes register B to a 7. Is that okay? In other words, it's showing me where the instruction is and what is the effect of the instruction. The instruction starting at location 05 did not change any one of the registers, but it changed the flags. And this is the way it changed the flags. And you can see the carry flag is a 0, the Z flag is a, excuse me, the other way. The carry flag is a 1, the Z flag is a 0, the sign flag is a 1, the overflow flag is a 0, the L flag is a 1. And then we get to the location 6, and I think that is our halt instruction. No, I take it back. 06 is the conditional branch instruction. So the question is, which way am I going to branch this time? I got two options. Either it is going to branch to label L1, or it's not going to branch to L1 and just continue execution. So can someone tell me after 06 where the program counter is going to go? Does it just move on to the next instruction, which is at location 08, or do you think it would actually take the branch and jump to location 09?
It would take the branch.
It would take the branch, and why?
Because the C flag is 1 in this.
That is correct. Good job. That is exactly what's going to happen. So the next instruction, indeed, is the halt instruction at location 09, instead of the halt instruction that is right after the compare instruction. Oh, right after the JCI instruction. Is that okay? So this is a slightly more involved process because you have to run logsim on the command line, collect the output of that, and then re-upload that file or re-import it into the trace raw data tab, and then you go to the analysis tab. So it seems like a lot of trouble for a simpler program. But this approach would allow you to actually look at the effect of every single instruction as the program executes, which means, okay, I'm not sure how much you know about using a spreadsheet, but if you want to look for certain things, okay, I'll give you an example. So let's just say that this is a really, really long trace, and you want to find out whether we ever got to location 05. Okay, does everybody understand what I want to find out? Okay, so it's a really long trace. Okay, I'm looking at this and go like, oh man, did I actually get to location 05 ever in this execution? What you do is you search. Okay, so you can now do a Control F. I think it's Control F would do the job, but Control G is better. So you do a Control G. It's the same thing. Okay, you go to Edit. You go to Edit, and then you go to Control H. Okay, I tried F, G, and H is the next one. Darn it. Okay, so you go to Control H, and it'll give you a lot of options. So what you want to do in this case is you want to find 05, but you can say where you want to search. So you can search your specific range, and in this case, the specific range is just your column A, because I don't care about 05 appearing on column B, C, or D. I just want to know, is 05 appearing in column A, right? So now we can specify just column A, and this is the way you specify, column A, and I think, that will specify the entire column. And then you have these miscellaneous stuff, do you want to match case, entire cell content, these are not relevant for what I'm trying to do now. And you click find, and did you find it? It found it, because it's highlighting it, but it doesn't change to that location. So let me do it one more time. Yeah, it did find it. It's just that it did not update the screen. So let me try that one more time. Find. There we go. Okay. So and when you read the instructions of today's lab, you will find out why I show you all of these options, because it is going to be helpful. Is that okay? And I'll just give you one more clue, okay? This is really important. This is a very useful way to find out how many iterations you went through a particular loop, okay? Which is what you're lab today has. Okay, it has a loop, and I want you to find out how many times we get to a specific opcode in the loop. Are there any questions? Let's see. We still got 2 more minutes. So I'll show you the super shortcutted version of doing all of the above because you guys are all thinking, Tech, are you really expecting me to remember all of these steps? Because I think there are 75 steps involved to get this done. And the answer is, well, this is actually what I have been doing before I got my own tool done. So my own tool is making this a little bit easier. It is called River Spider. I think last time I might have tried to demonstrate it, but it didn't work. But this time it's going to work. So I click submit and I give it the source file. So this one takes the source file and not the object file. So that means I have to use this source here and copy it to my actual file. Okay, so I need a little bit more time to set this up. So cat to cmp dot ttpasm, which is the source file. Paste that, put it all here, Control D to stop that. Okay, now we have the file. So, okay, now that we have the source file, I just have to say submit this thing, cmp.ttpasm, press the enter key, and just wait a little bit. Okay, it will do the assembling, get the object file back, run it in Logisim, collect the TSV file, re-upload the TSV file to trace raw data. And when we go to analysis this time, you will see the same thing, except this is actually cleaner because this particular mechanism goes through a special filter. So all the empty lines, all the blank lines are gone. And it's just one command. And all of you are going like, can I use the same thing? The answer is before this semester, it's hard, okay? Because this only works in Linux because I wrote the whole thing using Bash. Bash, by the way, is born again shell, okay? So someone, one of your fellow classmates from earlier, in an earlier semester, wrote a script to do this. Okay, so let me try to sign in again because it's actually in not Logisim, in Canvas. Ah, okay, just type in the wrong password. Nope, it was not. Jonathan was exceedingly successful in this class, but he was not the one who wrote it. Sorry? Yeah, he was the tutor. But the person who wrote this code was not Jonathan. It was Omir, Omir, Omir. So if I go to the class, I just put in the link just today. So if you haven't seen it before, that's because it did not exist before. So if you go all the way to the bottom here, you'll see a link to a GitHub, project. So if you read this, he will basically say what this is about. You do need to install PowerShell, and I'm not sure whether PowerShell is installed on these machines. If you do have PowerShell installed, you can probably keep everything on the thumb drive and just plug in your thumb drive when you're here. If you have your own PC, obviously that's not going to be an issue. You can just go ahead and install PowerShell. So it includes all the instructions that you need to get this done. And it's still involved, okay? There are still quite a few steps to get this done, but it can potentially save you time for the next 5 to 6 weeks or so. So you might find it worthwhile to do all of this. If not, you can always just do it the manual way, which I just did. And I have done it just the manual way for many years before I just threw up my hands. It's like, no, I don't want to do this anymore. I want to automate this whole process. And obviously, I spent a lot of time to automate the whole process, but it was worth it. Is that okay? So you don't need this today, okay? So do not try to spend too much time today to get this to work. Today's lab does not need this particular tool, but in the future, okay, in the next few weeks, I think it's going to be helpful. So with that said and done, I am going to give you the lab for today. And I'll be here to kind of help you depending on how you want to set it up. So today's lab is simple branching and code analysis. And that's why we have been talking about branching for the most part of today's lecture. And the access code is JXI, which is, okay, I see this new thing here, and I have to be super careful. And fortunately, I'm so careful because it reads right here, permanent marker. Now, why would they put a permanent marker right next to a whiteboard? They want to test me. I know they want to test me. Okay, so JXI is the access code for today's lab. And I'll give you guys till the usual time, which is 1:20 p.m. Yeah, make it at 1:30 p.m. Is the Computer Science Club meeting today? Okay, all right. So I think we should be fine. Yeah, I think most people won't take that long. All right, so you guys can go ahead and get started with today's lab, and I'll be here to answer questions related to the lab.
Is the test announcement on here, on the page?
Sorry?
The test announcement you put, about the second test?
Is it in the? It's in the announcement. So if you go to announcements, and then you can go to lesson plan for today, it's the attachment here. So it's an HTML file, you download it, and then you can open it with your browser. But I won't worry about it until after the lab is done.
Yeah, no, I
Yep.
just didn't see it.
Oh, okay. All righty. So without any questions, I'm going to stop the recorder.